One of the great inventions of our time that we all enjoy enormously is the bicycle. Many of us cycle around and it's a great pleasure. And one of the reasons why cycling is so pleasurable is because we have tires which are full of air. The pneumatic tire, working on the principle that air is compressible, is one of the great inventions of modern times. And I'm sure that anyone who rides a bicycle knows that it is incredibly inconvenient. The worst possible thing that can happen is to get a flat tire, because if you get a flat tire, that pleasant ride, the cushioning effect of this compressed air disappears completely, and instead of the tire bouncing along, it goes flat like that and makes a clump. So what do you have to do if you get a flat tire? You have to repair the tire, you have to put a patch on it, which is enormously troublesome, and then of course comes that great moment when you've put your patch on it, you have to pump the tire up again. And when you pump the tire up again, you notice that not only does the pressure increase, but there is another very important observation. And that observation, dear children, is the fact that when you pump a tire up, the pump itself gets quite warm. I don't know whether anyone's ever observed that, but I intend to demonstrate that now by showing you how to pump up a tire and also how to measure the temperature. Now, I will require one volunteer who can read a digital. That was the first hand that went up. Could you come down, please? Thank you very much indeed. Now, the reason why I want to volunteer, by the way, is because I want to do an honest experiment. I could easily have planted someone or got an assistant, etc. But my dear boy, come. What's your name?
Alexander.
Alexander, it's a privilege to meet you, Alexander. Alexander, this is a infrared digital thermometer. Could you just take it, right? Now, to read the temperature is dead easy. You just point it, okay, and squeeze the trigger. Point it down there. Okay, what's it reading?
27
degrees centigrade, okay, that's the temperature, okay? Now, could you just point it at that tire, for instance? What's it reading there?
27.
So let me just have a look. Let me just have a quick look. It might be, it shouldn't be. Let me just have a look. 22.
Oh,
okay, hold it down away. This is not easy and it requires, this is fantastic technology, but it gives you an instant reading of the temperature. Alexander, could you just point it once again to there?
21.
21, okay? That's the temperature in this room. That makes sense. Now, Alexander, what I'd like you to do, I'm going to pump up this tire, and I'm going to ask you to take readings of the temperature when I tell you to, okay, at a certain point on the tire. So here we are. I'm going to give it a total of 150 strokes. And I'm going to ask Alexander to, excuse me, while I tighten up here we are, tightening my tire on there. And what I want you to do, Alex, I'm going to hold it down here, right? But I want you to measure the temperature of the pump itself. That's the important bit, okay? So could you just measure the temperature of the pump there where I'm not holding it? What is it now? Should be about 20, look, there, about there. What is it at the moment?
22.
22, thank you, okay? I'm now going to give it 100 strokes, okay? So here we go. And you'll measure it after 100 strokes, okay? Right. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 23, 24, 25, 26, 27, 28, 29, 30, 31, 33, 34, 35, 37, 38, 9, 40, 41, 44, 45, 46, 47, 49, 50, 1, 2, 3, 4, 5, 6, 7, 8, 9, 60, 1, 2, 3, 4, 5, 68, 9, 70, 1, 2, 3, 4, 5, 78, 80, 1, 2, 3, 4, 5, 6, 7, 8, 9, 90, 1, 2, 3, 4, 5, 6, 7, 8, 9, 100. Now measure it there. Closer in.
32.
32, okay, measure it right down there.
31.
31, okay, look, let me just have a quick go. It possibly higher. Yeah, 31, 32, 33. Okay, thank you very much, Alex. And that was very kind. Now, the point is... Thank you very much. The point of having Alex is to actually show that I wasn't messing around. I'm a bit out of breath because it's quite hard work pumping the tire. But the point is there's a significant increase of about 10 degrees, the tyre has gone, the pump has gone up. Now that, you see, is because when we pump up, the energy that we put into the tyre actually is converted, or into the pump, is converted into heat energy, because the energy can't escape. We call it in physics, we call it adiabatic compression. Adiabatic means that the energy has nowhere to escape, so therefore all this energy here goes into raising the temperature of the thing. Now that idea of raising temperatures by compressing had been noted by people thousands of years ago. We don't know how, but the honest truth is it led to, because people who saw this effect when they were using pistons in simple, I don't know, again, we don't know, but the historical facts are proven that people would have noted that pumping or compressing air makes it get warmer, and they then would have experimented to see how hot they can make things get. And we know that over 2,000 years ago, people had already developed a technique for actually using this compression to make temperatures big enough to actually start a fire. So, and this was called a fire piston. It was a type of technique used by thousands of years ago. And what I wanted to show is an example. This is a teaching aid, and I'm not sure it's going to work. These are very difficult equipment to work, you see. But what it is, this is a piston like that, where there's a piston here, and there's a cylinder, glass cylinder, and there's a tiny little bit of charred cotton in the bottom. And I'm going to squeeze it very hard indeed. I'm going to ask the light to be dimmed, and hopefully you'll see a little flame as the temperature reaches about 400 or 500 degrees centigrade. Could we dim the lights, please, so that we can just see whether you can see a little flash of light? And because these fire pistons, which were used by tribes in Southeast Asia, okay, I'll have a go now. So look to see whether you can see the flash. 1, 2, 3. Did you see that? There. So that's so you saw the flash. So the point is, we got the thing. Now that momentarily, that flash, that shows you that the temperature must have got to about 400 or 500 degrees centigrade. Now, what we can do, this illustrates the principle. You could see the flash in there, but you can actually use that technique to actually light a fire, which is what they used to do. Now, I'm not going to spend too long on this because it's a very tricky one, and this is the object of this is actually making fire by work being put in. It's not firework, it's work making fire, but that doesn't matter. The words can be interchangeable. And it's an excuse to show you something you may not have known about. Now, I've got here a fire piston, which is commercially available. And what we do on this, there is a tiny little bit of charred cotton on there. And I'm going to have one go. This is very, very difficult. And I've tried it, and I will put it in. And when I pull it out, if we're lucky, there might be a tiny bit of a glow on there. If there is a bit of a glow on that charred cotton, I'm going to try and tip it out into my tray here, which contains more charred cotton. I will then blow on it, and hopefully it will start to glow, and maybe we'll be able to start to make it catch fire. But that's the honest truth. This technology was known, and apparently in 1745, fire pistons were brought over from Southeast Asia, and they were used as lighters. In addition to using friction or flints, they were also used for lighting domestic fires before the safety match was invented. So I'm going to put my piston in here. I'm going to put my piston, my plunger in there. I'm going to whack it one, and hopefully we'll observe a little glowing ember. That's the very difficult bit. 1, 2, 3. There we go. Nope, didn't work. Let's try it. Nope, not working. Let me just have one more. I don't like to give up, you see. I will try again. As I said, this is extremely difficult. I haven't had much time to practice, unfortunately. But these things are commercially available. And if anyone wants to sort of, look these things up, there's a lot about this. Information is available on the internet and so forth. And it's very interesting. I'm just going to take out that bit of charred cotton. The important thing is to make sure that you develop a good pressure. I'll tell you what, I'll put let me just try another little rubber seal here. I have a rubber seal here, which these rubber seals, they don't last because you apply enormous forces to these things, you see. So we'll just quickly see if I can get another one out, and I will have another go. I don't like take defeat too easy. So I'll just unscrew this here quickly. We'll unscrew that one there, and I think that one's actually quite knackered, so maybe maybe we will get a result. Maybe we will get a result. You apply enormous forces, and they always send you a set of spare seals, you see. So I'll put this one on here now. I'll put another one on. We'll screw that in, and we'll put another tiny bit of char cloth, and then we'll see how it, and then we'll just have one more attempt. There is a chart. Whoops-a-daisy. Sorry, this is all rather slippery with my gloves here, but I do think that I don't like to give up, let's put it this way, after just one attempt. So there is so I've got my, if you do it up too tight, then it squeezes it, it's all, right, there we are. So I've got that on there, and we've got, you must lubricate it to ensure that you've got a full-scale seal on it. And what I'll do now, I'll take another piece. There's a tiny piece of charcoal. They're very cleverly made, these things. They machine them. There's grease in that end. That's for lubricating the seal. And in the other end, there is a tiny bit of, there's your char cloth, you see. There is your black charred cloth. It's basically a piece of cotton wool or cotton which has been strongly heated in the absence of air. So it doesn't catch fire, it simply carbonizes. So I'll put this now into my piston here, put that onto the end of my piston there, a tiny piece of this char cloth here, and I'll just give it one more attempt. I did get it to work earlier today, so we'll just see, there we are. We'll put it in there now, and now we'll just screw this top back on again, and we'll see whether we can get it to glow. If it doesn't, we'll move on, because as I said, these are not easy experiments to be attempting with the relatively little experience I've had. But nevertheless, I think you ought to know about these things. So just a tiny bit more Vaseline on there, tiny bit more lubrication there, just to make sure that we get, the purpose of that is to get an absolutely airtight seal so that the air can't escape. So here we go. We're going to give it one more attempt, and hopefully it may come out glowing if we're lucky. So, something's not right there. Something's definitely not right there. Now, why is that gone so... Hang around, there is... Yes, we're getting there, I hadn't quite... Whoops-a-daisy, we'll get a result. I know why. You need to screw it up a bit more. I'm getting a result now. It's got to feel springy, you see. There we are. We're just getting it in there now. And let's just have a... Yep, that's it. We've got springiness, so that means that there is a seal. We now... 1, 2, 3... And then pull it out. Oh, dear. Never mind. Let's have another go. Nope, hasn't worked, but please, that's the thing. I'll carry on. Now, no, please. I'm going to now tell you, but this is the important thing. We use this principle of setting fire to things purely by compression on an everyday basis in motor cars. And that's what we use in diesel motor cars. Diesel motor cars work on the principle that the fuel, the diesel, mixed with air, is compressed, and it is set alight purely by the heat generated by compression. Now, what I've got here is I've got a model diesel motor, which I'm going to try and start up and see if we can power our little thing. Now, I do have to repeat, this is another very, very difficult one, and I have actually got it to run twice today, but I have to say it may take up to 5 minutes to start. So I'm going to start on the procedure now. It's and when it works, it really does make quite a noise. We're now priming it up. I'm drawing some fuel into the piston. It's a very simple thing. And then, now it takes up to 200 attempts to do this, okay? But it's worth it. And the thing is, you think nothing's going to happen, and then suddenly it springs into life. And the reason why is because as I'm doing this, I'm warming it up slightly. And as you warm it up, then you actually increase the chances of ignition. So, as I say, I've just added some more fuel directly. Right? This is normal, by the way. These are and one of the reasons why these went out of fashion was because they're so very difficult to start. And then And they started, what people started doing, they started putting glow plugs in and all sorts of other things. But I wanted to show today, anyone can start this with an electric spark, you see, but that's not the point. The point is to use the heat generated by compression. And that's what I'm doing here. As I'm turning, every time that little piston is going up and down inside the cylinder. And if we don't get it to work now, I will come back later if I have to. This is very much work, and I still haven't finished. I'm only about a third of the way through my efforts. So if you're wondering what the hell I'm doing, let me tell you a little bit about this. This is called a diesel motor. Now, you'll notice there are two kinds of fuel you can buy today. You can either buy diesel or petrol. Have you ever thought why they're called that way? Well, I'll tell you. Diesel fuel is called in honor of the man who invented it. This technique, by the way, invented this technique. His name was obviously Rudolf Diesel. In fact, this is the Rudolf Diesel carriage I have built for you. Do you know what? It's not beginning to sound anything at all. But the things, there is never any, this suddenly, what happens is, it's suddenly, when you think you've lost all hope, which at the moment I think I've lost, Diesel invented this. And why did he do that? Because he was living in the late part of the 19th century when they were looking for more efficient ways of powering machines than just steam engines. Steam engines burnt coal, and coal had to boil water to make steam. I told you it starts. Oh dear, I was just about to launch into a flight. Ow! So here we are then. Ow! Now then, here we are. The diesel carriage. Oh dear, it's going the wrong way. That's really funny. No, I had the propeller going the wrong way, but you must admit it was fun. And that's very odd. It's very odd that it started going backwards, you know, because I'd noticed that before. As I said, I haven't done this many times, as you can see, but it does go very fast indeed when it goes, and I wanted to just shoot it across the floor. But idiot Szydlo had started making it go backwards. That means that definitely needs another little injection of fuel there. And let's see. I don't know why on earth it started going backwards for some reason. I'm not going to waste much more time because I think you've seen it. You've seen it go, and that's the important thing. And I think we'll move on to the important things in life, which is what is chemistry at the end of the day. Let's just see. I'm not sure whether it's going backwards. Isn't that bizarre? Well, at any rate, a most bizarre thing I've invented. I'm not going to repeat that, but I must confess this is I've clearly invented something new. A propeller which I think was going in one direction started going in another direction. Now, the point I wanted to stress is diesel engines work purely on the principle of compression. It's that compression which gives you enough heat to actually make it work. So that's to make it ignite the vapor, which is an extraordinary achievement. Diesel engines are fundamentally different from petrol engines, because in petrol engines you have a spark plug. The compression alone does not generate enough heat to set it on. Now, the fact is that fire, anything to do with fire, is the quintessential topic of chemistry. Chemistry is that branch of science which is, for which fire is one of the most important reactions. But let's just remind ourselves of what chemistry is as a science. Chemistry is the science of substances and how they turn into different substances. Now, at the moment, albeit, you know what, it's possible that I've actually got there we are, substances turning into different substances. And as you see, I've had a very, very panicky day today. But you see, we can recognize very frequently, these changes by the color change. And so we're making a new substance on every occasion. Now, I've got some more color changes to show you here, just more examples of chemical changes. In these gas jars, I've got sulfur dioxide in this and potassium permanganate solution. And we can once observe a dramatic chemical change as the potassium permanganate is decolorized in the presence of the sulfur dioxide. So that's a redox reaction. Here, we've got acidified dichromate solution, another example of a redox reaction, and you observe the beautiful change of color from orange to green as the sulfur dioxide reduces the chromium from the +6 to the +3. Here we have some universal indicator. Sulfur dioxide forms an acidic solution. It also has a choking smell, which I'm beginning to enjoy at this moment. And what you observe here, of course, is the acidity, a weak acid, sulfurous acid. Now here I've got one of the most vile gases that the universe has invented, hydrogen sulfide, bad egg-smell gas, but it does a wonderful precipitation reaction with lead nitrate. Please watch carefully as I pour it in. And you'll see the immediate appearance of a dark black precipitate of lead sulfide. So these are examples of chemical reactions in waterworks. You could see water working to make a chemical reaction happen by virtue of acting as the solvent for the substances dissolved therein. Now, I wanted to move on to this experiment here, which is another experiment involving both chemistry and physics. And the principle, we're on the theme of waterworks, but from 2 points of view. One, water acting as a solvent, and the other, using atmospheric pressure to generate a fountain, which will be a principle of physics. So, what I wanted to tell you is, first of all, that you all probably know that water can dissolve certain gases. And the gas that you're most familiar with, that you drink on a regular basis, is any kind of fizzy drink. If you have, for instance, carbonated water, that fizzy water, the bubbles are actually bubbles of carbon dioxide. Carbon dioxide is reasonably soluble in water, but if you pressurize it, then it becomes much more soluble. Now, there are two gases I wanted to introduce you today, which are amazingly soluble in water. One of them is the gas ammonia. Now, I have here a bottle of concentrated ammonia solution. Now, the solubility coefficient of ammonia in water is about 600 to 1. That means that 1 centimeter cubed of water dissolves about 600 centimeters cubed of ammonia. And if I take the top off, you can't see anything. There is ammonia gas coming off because this is saturated. It's reeking of ammonia. I can't even smell it, fortunately, but I will shortly. Oh, did you see the top come off? Now, the reason why the top came off is because there is so much gas being produced. It's saturated, so that ammonia is pushing it out because it's quite warm in this room. Now, I have here a solution of another liquid, another gas dissolved in water, which is also very soluble, and this is hydrogen chloride gas. Now, if you dissolve, that's got a solubility coefficient of about 400 to 1. That's 600 to 1, about 4. And if you take the top off, you will notice a tiny little bit of steam. It looks like steam. It's actually tiny water droplets which the gas dissolves in very rapidly. Now, the interesting thing about these two is this is a strong acid, whereas this is an alkali. It's actually a weak alkali, but by gum, it's concentrated. And acids react with alkalis in neutralization reactions. So please watch carefully this most curious reaction where two gases will react to make a solid. As I wave them together, you'll notice a dense white smoke being produced. Now, that dense white smoke is actually ammonium chloride. And what I'm going to do to show you is if you actually mix the two together with those very concentrated solutions, then they give you a most violent reaction, emitting a huge quantity of ammonium chloride smoke. So please watch carefully as I now pour some strong ammonia solution and release a huge cloud of ammonium chloride smoke. So we pour that in, and there you notice a violent reaction, you see. And all of that's neutralization, and that is relatively harmless ammonium chloride which has gone into the air. Such is the power of the chemical bonds that we can observe the wonderful air currents in a splendid ventilation in this room. Now, allow me to explain what we've got in here, because you see, I've just shown you a strong solution of ammonia in water, and what I've now got in this flask, I wanted to tell you, this flask is full of bone dry ammonia. I made it this morning. And what I'm going to do is, that is full of ammonia, and I have inverted the bottom tube, goes into a trough which is full of water, which has got a few drops of bromocresol green indicator in it, and it also has a few drops of hydrochloric acid to make it yellow. Now, I'm going to open the bottom, and what I wanted to tell you is this. I'm going to open the tube at the bottom, and then I'm going to suck some water into the flask by cooling the flask down. We're now using the principles of physics, you see, and we're going to use this as a sort of a thermoscope. At the moment, the water is at the bottom, but I'm going to suck the water up by cooling this down, and gases contract enormously when they are cooled, and as the water rises, once it gets to the top of this tube, you will then observe all the ammonia in here will instantaneously dissolve into those few drops of water. And when that happens, then the rest of the water will be forced into the flask to hopefully create a little fountain. I'm going to cool it with a liquid nitrogen, which is the most effective cooling agent. At least I hope it is. We're seeing what's going to happen. It's going to start rising. There it is. It's just beginning to rise. If liquid nitrogen doesn't work, I've got something else. I've got ether. So please, we've got plenty of tricks up our sleeve. We must get a result here. We're cooling it down. Can you see the level is rising? It's rising. It continues to rise. There it is. It's getting higher. It's now gone 2/3 of the way up. 2/3 of the way up. It's now going inside the rubber bung. But the moment that water gets, there it is, it's almost at the top now. Let's leave it. There we go, and there's our fountain. So we now have the classic ammonia fountain. The ammonia has instantaneously dissolved into the water, creating a vacuum. And the color changes as well, because ammonia is alkaline, as I just explained to you, whereas the water here was slightly acidic. And I've got an indicator in there to show this difference, you see. So there you see an example of Waterworks in action, a fountain created both chemically and physically by the pressure of the air forcing it in. Now, having done a couple... No, please. We'll do the applause later. I'm in a bit of a hurry. I wanted now to turn to my favorite subject, which, of course, is fire and fireworks. The water stuff's quite good and pretty, but fireworks is where it all really does begin. And I wanted just to explain to you a few things about gunpowder, because gunpowder, of course, is the essence of any firework mixture. And I wanted to tell you, and I'm sure you all know, or most of you all know, that gunpowder was discovered or invented in China probably about 1,000 years ago. We're not quite sure. But what I think people are interested to know is how the dickens was gunpowder invented? You can't sort of imagine someone walking along the road and saying, oh, look, let's mix a few things together, because I've actually got the things here that make gunpowder. Here they are. This is charcoal, finest quality willow charcoal. This is sulfur, the element which is associated with volcanoes and volcanic action and occurs naturally in the ground. And this here is the magic ingredient which makes them burn better, potassium nitrate, otherwise known as saltpeter. How on earth did people of thousands of years ago strike upon this mixture, these substances, etc.? Well, we can only surmise. I'll just give you a few pointers. People have been burning. Burning was one of the great achievements of our early traditions, conquering a fire, as I attempted to do here. But the fact is that conquering fire, and people always wanted to improve things. And it is undoubtedly true that in some parts of Southeast Asia, it is a well-known fact, crystals like this actually grow out of the soil where there are many cattle, where cattle urinate and the climate is hot. Now, these crystals, exactly like this, were actually manufactured, this is potassium nitrate, were manufactured on an industrial scale until relatively recently in India and in other countries in Southeast Asia. And the reason being that a huge number of these crystals grow. They grow Probably because urine comes out, the cattle's urinate, the urea gets converted to ammonium compounds by bacterial action, that is then oxidized by atmospheric oxygen to nitrates, that then reacts with wood compounds, wood dust or wood charcoal to form potassium nitrate, and this is it here. And this occurs naturally, as I said, it grows out of the ground. Now, without doubt, people would have probably found that where these small crystals like this were growing, the charcoal embers of a fire would have burnt better. They would then have probably mixed the ingredients together, got a better result, and then using sulfur there, added that, and eventually. But this is a process which, I repeat, took hundreds, if not thousands of years. We're not sure of the exact history of the discovery of gunpowder. But enough said, let's now actually have something. So if you have a crude mixture, gunpowder is made of 75% biomass of potassium nitrate, 15% biomass charcoal, and 10% biomass sulfur. Those are roughly the proportions. These proportions have been recorded since the Earth for quite a long time. We've known about these proportions from our readings of ancient scripts. Now here, I have those proportions mixed up, but in a slightly crude manner. This was this type of proportion, this type of mixture was called serpentine powder. And the Chinese often interpreted things. They had a very, very great philosophy of nature, a profound philosophy, in which they explained all sorts of happenings and the theory of opposites, etc., etc. But I don't know much about it, but I wanted to tell you that they would have interpreted this as sort of dragon type of behavior. And if we now light this would have been, this is actually the translation. This is called serpentine powder, and this is crude serpentine powder, simply made by mixing those ingredients without any particularly special effect or trying to. And you'll notice it burns like that. It's not particularly, but you say, well, that's not exactly gunpowder, but it's better than just burning a bit of charcoal or a bit of sulfur. It's quite pleasant, it's making a lot of smoke and sparks, and it's certainly better than burning the ingredients without the added nitrate. Now, please observe, can you see this yellow deposit here? That shows you that that's not a brilliant combustion. Nevertheless, it was. So what they did, being very intelligent, they would have said, let's mix these ingredients together more thoroughly. And the way we do that is by increasing the surface area by grinding them. So they then started grinding them, and if we grind them and mill them together, this is now milled serpentine. No, that's coarse. Sorry, I've got the same one. Let's make sure I pick up the right one. This is milled serpentine powder. This has had 8 hours in a ball mill, and I'm going to pour a similar thing. So this is now much more finely powdered, and let's observe now how this burns. You see, so this has much, much tinier grains, and as I said, we should observe a much larger surface area. Let's observe this and compare the difference. So there it is. You see a much smoother combustion now, and you see also, significantly, there is no residue of this yellow, or the yellow specks are tinier still. However, being very intelligent, they said, can we improve this still? Now, using baking technology, which is when flour and ingredients are mixed with water and kneaded together, they took these ingredients here, which had been milled, and they kneaded them together, pressed them through a gauze, and ended up with corned serpentine powder. And this, I'm going to pour a small quantity of this corned serpentine powder there, and I'm going to set fire now to this. And please notice the difference. So this has now been milled, caked and dried, milled, pressed and dried, and let's observe there. And you notice here we have, so now what we have is actually full-scale black powder. And let me remind you, the Chinese had invented this 1,000 years ago before modern chemistry. This was just done by intuition, by experiment and deduction, by huge natural intelligence. Now, having invented something like that, the first thing they would have said, brilliant, what can we do with it? Because this would have been very exciting. This would certainly not have been invented overnight. It would have taken some time. Excuse me, I'm just going to dispose of my gloves. And when things burn rapidly, the first thing you want to do is to confine them and put them into some sort of prison to see if they can, how they burn in a confined space. And they started inventing or making firecrackers. So I'm going to make a firecracker for you now out of 2 sheets of A4 paper, which I have glued together. And I'm going to set it off and we can see the effect. They, of course, would not have used this type of technology. They would have probably used bamboo, which has chambers in it, which are separated at nodes, and they would have hollowed out the bamboo, filled it up, and set it off and made firecrackers that way. But I'm making a tube here, and I'm going to now reinforce the tube by putting some tape on it like this. So we're going to put the tape on it like this, you see, put the tape on, and so we're first of all making a tube or a prison for our fire serpent. The Chinese would have probably referred to this as a sort of a fire serpent or a fire dragon, and they would have said, let's stick him in a cage and then set him on fire and see what the dickens he gets up to. Well, that's exactly what we're going to be doing in just a second. So here I am. I've now sealed this up, you see. I've made a bit of a tube here, and we can now pull this tube out here. Now, what we can do next is we can cut the end off because we're going to seal it up. We're going to seal it up and then put some of our powder in. So if you don't mind, I'm going to bend this over like this now, and then I'm going to seal it up with by wrapping more tape around it here. So we're wrapping the tape around here to create a secure prison for our powder, which we're going to put in. So there is we have now made our tube. We can now put a rod down just to make sure that we have this there. And now we're going to put in some of our powder. So we're putting in now some black powder. This is simply gunpowder. It is that substance which has had a profound effect on human history through its use in warfare, but also for people enjoying it in pyrotechnic effects. That's probably 6. I'm not really counting. It should be 7, but I put in probably a bit more. And I must always make sure that there is enough to achieve the desired effect. Now, what we're now going to do is to measure the depth in there. And we see we've got the depth is down to there. So we've got quite a decent bit of powder in there. And we can now trim off the top like this. And now we need to put a fuse in. We need to put a fuse in. And please allow me, I'm just double checking. Yes, I'll just trim a tiny bit more off, and I have some fuses here, and we will now pop a fuse in, and then we will bend it over and seal it and see what happens. So there it is. I'm now going to bend it over like this, you see. Bend it over. I hope the fuse has gone right down. Yup, it's sticking into the powder like that. And I'm now going to wrap this up once again with more tape. So we can now say we have put our fire serpent, fire dragon, into a prison. And that's that firecracker, of course, which we made. So here it is. I have now made a firecracker like this, you see, and I'm going to now set fire to it and see what effect is achieved when the serpent, the fire dragon, escapes from the prison. However, I'm sure you all recognize that to do this on the open hand would not be a very bright idea, because the fire dragon will be very angry. And so, for this purpose, I have here a specially constructed, we call this a banger cage, and it's a special cage where we put in our firecracker like this, and then we set it on fire, and we put the ends on. Now, for this purpose, I will be putting on safety specs, and I will also be putting on a pair of leather gauntlets. I've got lots of leather gauntlets and all sorts of safety equipment, so you must excuse me. And I will set fire to it, and I'll tell you what this cage is all about. This cage has a shelf in the middle. It has a shelf in the middle, which is here, made out of and so our cracker is resting on the shelf there. Both the ends have holes in them. So and I'm going to hold it up like this, you see. Once it's on, put the end on, and you may see some sparks shooting out of the end. So we have to take care that no debris lands on anyone. So here we are. I'm now going to, excuse me, I'm just going to find where the end is. It's in there. I'm going to set fire to it, put the end on, and we'll listen to see what sort of effect occurs when the fire dragon escapes. So here we are. We're now holding this. We're now ignited. We have ignited the fuse, and there it is. So there you see. There it is. Our fire dragon has now. Our fire dragon our fire dragon, you see, has escaped and left a huge hole there. Now that you see, that type of effect caused a great deal of merriment, and the science of pyrotechnics and rocketry developed to a very sophisticated stage. However, it was one of the greatest triumphs of chemistry that entirely altered the way we burn fuels, and gunpowder was probably one of the ways in which it helped to make this remarkable discovery. Now, that discovery, as I said, was a discovery of oxygen, the idea that air is a mixture of gases and not an element, as people had thought for thousands of years. And therefore, if you don't mind, I'm going to move things away because I've gradually got to make space for other experiments. So if you don't mind, I shall be occasionally turning my back to you. Now, once people had discovered oxygen, oh, I wanted to tell you, I've forgotten, there's another rather fun gunpowder here which I've got. I wanted to show that it is possible, and the Chinese had also done this. They had found it was possible to add other ingredients to the black powder, which I demonstrated, and I just wanted to show you an effect with one of these. Now, I'm looking for a spatula. We don't want one which is too small. This wouldn't put enough of the powder in, so I'm going to use a slightly larger spatula. Now, this powder which I've got here, it looks like normal black powder, but it has actually had special bits and pieces of metal and other things, glues and oxidants added to it. And this type of effect had also been achieved. Now, I've got to move this out, and I've definitely got to wear my safety goggles for this. This is really quite a nasty one. Please excuse me, I'm going to be tidying up. I'm going to be tidying up as I go along because we must have a tidy bench, and I shall definitely be wearing these and this. Now, I'm just going to set fire to that, and notice the difference. This is black powder with metal granules added to it, and then we shall move on to the theory of oxidizing agents and the age of modern chemistry, and how oxidizing agents have improved our abilities to make use of fuels. Oh, sorry, this splint is not feeling very well today. Here we go. Now, I'm just going to load it in, but watch, this is now, I'm not sure whether, I can't see it. I'm quite terrified of this because when you see, we almost, let me just take another splint. We must always take great care with these things. This is really quite a nasty little powder. If it doesn't work, I'll make sure I'll get it to work somehow. It goes rather without, but without warning, I meant to say. Sorry, no. So there you see the effects that can be achieved. The effects that can be achieved by adding other ingredients. Now, I wanted now to move on to the field of modern chemistry. Oh, that's rather, actually, it's not too bad, actually. Oh, got it. Now, I wanted to move on to the field of modern chemistry and explain to you that we now, thanks to the discovery of oxygen, we can now make use of powerful oxidizing agents, subjects, things which make their ingredients, which add extra oxygen and which make the thing burn much better. So I've introduced you already to potassium nitrate. Potassium nitrate, chemical formula KNO3, used in black powder, used as an oxidizing material for in a low grade. However, I have here two other oxidizing agents which are also used in pyrotechnic mixtures, and they are both very rich in oxygen, obviously. One of them is potassium chlorate. Now, I'm going to show you potassium chlorate here. It's I've got it in a bottle labeled potassium chlorate, obviously. And if you don't mind, I'm now going to borrow a sheet of paper. Actually, no, these papers are too pretty. I need to make up a little mixture, so you must excuse me while I know what, I'll use the back of my program, because quite honestly, there's no much point in reading my notes at this time, is it, when I'm halfway through? They're not going to help at all. So we'll just have to rely on good. Now, what I've done is I'm going to mix some potassium chlorate, which I've got here. Let's just add a tiny bit more, a powerful oxidizing agent, and I'm going to mix it with all things with icing sugar. Now, icing sugar, of course, looking at it chemically, actually is a carbohydrate, and it's used to provide energy. Energy in when we eat it, of course, etc. Now, I'm going to mix a small quantity of icing sugar here, and I'm going to make it provide energy, but not through the process of respiration, but through the process of combustion, which is far more fun. So what we're going to do is we're going to mix in our potassium chlorate now with the sugar, and then I'm going to put it into my crucible. Now I shall then add to it, let me just make sure very carefully, oh dear, actually I can still read my program notes. I have no intention of burning this, I'm simply using it to mix my powder. Now, there we are, we'll put that in there and just tap it down a little, and now I'm ready to read my instructions should I go wrong. And what I wanted to do now is to, I'm not sure that I put enough of the chlorate, but it's too bad, we've got to try it out. I'm going to add to it another powerful oxidizing agent, which is concentrated sulfuric acid. It's certainly not used in fireworks, but it's used for making very high explosives. And what I wanted to do is, one drop of this will react, it'll react with potassium chlorate to make chlorine heptoxide, which is unbelievably violently decomposable, and it also releases a lot of fire as it does so. And that should set fire to the mixture. So one drop of concentrated sulfuric acid hopefully will release the oxygen and make the sugar start to burn better. Sorry, that was a small drop, maybe a... Oh dear, I didn't put enough potassium chlorate in. There we are. Sorry, it was 3 drops. 3 drops. Never mind, it's off the mark. And there it goes, you see, sugar burning with the oxidizing agent, potassium chlorate there, making it burn much better. So there you see a little bit of charcoal. It's carbon which is coming up, you see, being released in quite a violent manner. I hadn't actually mixed it in very thoroughly, but that, you see, was a nice pyrotechnic effect. It's carrying on, in fact. Let's see. Now, while we're leaving that to cool down, another powerful oxidizing agent used in pyrotechnic mixtures is potassium permanganate. And potassium permanganate, chemical formula KMnO4, also releases its oxygen very readily, especially in conjunction with glycerol. Glycerol is a heavy-duty alcohol. It's actually a substance which is used in cough syrups, and it entirely has quite a nice sweet taste. And there it is. That's glycerol. Glycerine is a trihydric alcohol. Propane 1,2,3. Triol is the chemical name. And the fact is that potassium permanganate will spontaneously oxidize that, and that will then catch fire. Now, there it is, our glycerine is now burning. Once again, another spontaneous combustion. So there we have examples. Then there are 3 oxidizing agents or used in fireworks: potassium nitrate, potassium chlorate, and potassium permanganate. And each one of them capable of supplying a lot of oxygen. Now, what I wanted to say, each of those contain oxygen chemically combined. But here I have a flask which is full of pure oxygen, and it is possible for some substances to burn very, very effectively in pure oxygen. And I'm going to now show you the combustion of a very unusual substance, which is very difficult, though we will ask if once this is underway, we can dim the lights to improve the visibility. And what I've got to show you here is the element phosphorus, white phosphorus, unbelievably dangerous, unbelievably flammable, and it's stored underwater. And what's interesting about, do you know what, if you don't mind, I'm just going to tip the mess. I have to keep the place tidy. We'll just put the flask on there. That's not too hot, so we're okay there. And allow me to explain. White phosphorus was discovered accidentally by the German alchemist Hennig Brandt in 1669 in Hamburg. He was distilling horse's urine with charcoal in an attempt to make the philosopher's stone. The whole flask started glowing, which is what you will see shortly, and he had thought he had made the philosopher's stone. In fact, he had discovered white phosphorus, and that too plays an important role in everyday lives, as I will shortly explain. But the most important thing, this is an unbelievably toxic element. There are 3 forms of phosphorus: white phosphorus, red phosphorus, and black phosphorus, and this is by far the most deadly. Now, what I'm going to do, I'm going to take a pair of my pincers, my tweezers here, and it's stored underwater because the moment I take it out, it will start trying to catch fire. It will start smoldering, but don't worry, all is in hand. We shall now pop it into our jar full of oxygen there. and put the top on. And now I shall set fire to it using my long glass rod. Now, phosphorus is so sensitive to heat that it will catch fire even if you touch it with a warm glass rod. Now, when I touch it and it starts burning, please there we may extinguish the lights, and you will observe the beautiful flame, the beautiful color that will be produced as the phosphorus burns in oxygen. So there it is, and please watch carefully. We're now covering this up like that. If we turn the lights off, so there we have, you see, the element phosphorus burning in pure oxygen and releasing a dense white smoke of phosphorus pentoxide. So now what's interesting, the element phosphorus itself is unbelievably toxic and by that virtue incredibly dangerous, but the substance which it has produced, can we have the lights back on again, please? Thank you very much. The substance which it has produced in its reaction with oxygen is actually, we actually drink it on a regular basis. You see, this white solid here is phosphorus pentoxide. And when you dissolve phosphorus pentoxide, you make phosphoric acid. And if you read the label on the Coca-Cola, the Pepsi-Cola, or any kind of cola you drink, you will see they contain phosphoric acid. And phosphates are very good for you because our bones are made of phosphates. So there, once again, the nature of chemical change is such that it can do all sorts of changes. So substances which are toxic in one circumstance become eminently necessary for life once they have been chemically changed. Now, what I'm going to demonstrate now are some pyrotechnic effects. And I've shown you the fundamentals of pyrotechnic art, the use of oxidizing agents and fuels. But I'm now going to show you some pyrotechnic effects, and I'm going to start off by just illustrating the principle behind a bang or an explosion. Now, in order to demonstrate this, one could, make another firecracker, but that's not the purpose. It's to show you the idea that the reason why bangs occur is because there is a sudden release of energy when a mechanical device is broken asunder. Now, what I've got here, I've got 3 bottles from mod drinks, and I'm going to pour into them some liquid nitrogen. Now, please, I can't see what I'm doing. There's so much steam around here, but I'm sure I will get some of it in. Now, what I'm going to do is to tell you that when a liquid boils, it hugely expands in volume by a factor of 700 or 800 approximately. So, in other words, if I've got, if I'm pouring in, let's say, 100 cc's, 100 centimeters cubed of 100 cent. Oh, I've got a huge amount in here, far more than I intended to have. Let's just pour some in. Not that it matters that much, but it's just a waste of liquid nitrogen. Sorry, I'll just pour some back in there. There we are. Let's just get it. I want to have quantities which are approximately equal. Just pour some of that back there. I couldn't see what I was doing. You see, there was so much steam. Now, we've got the top on here, you see, and we'll just put that back on there. We have got now 3 bottles. Now, what I'm going to do, I'm going to put the top on. Now, and they're boiling. Temperature liquid nitrogen minus 196. This room's about 21. So they're boiling. What I'm going to tell you is this. As the liquid boils, this will carry on boiling. Its volume will increase by about 700 or 800. Now, if I've got 100 cc's, that will go from 100 to 80 litres, right? That is one hell of a big volume. There's 5 litres in there. Imagine 160 of those flasks. No, 80 litres. That doesn't matter. A large number of those flasks. Okay, I'm getting tongue-tied with my numbers. Mental arithmetic is not good. I'm sorry about that. But the fact is that this will increase. Now, as this starts to take up, starts to expand, so it will start to develop an enormous pressure. Now, as it develops an enormous pressure, so eventually the bottle will no longer stand the pressure. And even though the bottle is made of fantastic polymers, thanks to the science of chemistry, they can take really a very, very high pressure indeed. These polymers, their chemical bonds are very strong. It's the genius of the science of chemistry chemistry, their invention, they will not withstand what's going to be on offer from the boiling of liquid nitrogen, and they will expand to such an extent. Sorry, I'm putting the lid on there, and I have to warn you that they will explode with considerable violence. And if you're afraid of bangs, you should definitely leave now. Now, I'm in the middle of talking, and I can't possibly appear to be a coward though I am. And I shall now place this one in here. Now, I have to tell you, it takes about 7 minutes before the effect occurs. So while we're waiting for the effect, demonstrating the physical process of a bang, we shall continue, and you should be all timing on your watches. Now, before the bang occurs, you will hear an ominous cracking sound as the bottle is reaching its maximum tensile strength and it's about to burst. So I do warn you, the bangs will be very loud when they occur. Now, the next thing, so how to make a bang. The next thing, how do you project fireworks into the sky? Well, here we have two techniques. One is when you see beautiful fireworks displays with stars bursting all asunder. They are put in by mortars. I have here a simple mortar, and tell you, and the principle of the mortar is that you burn a fuel at the bottom, a huge amount of hot gas is liberated and throws out your pyrotechnic ball, which explodes high up in the sky. Now, I'm going to be using this mortar not to propel a pyrotechnic mixture, but simply a few ping-pong balls. It would be quite inappropriate to try and propel a firework mixture into this, the ceiling of this beautiful building. Now, what we have, so once again, it's a tube which is sealed at the bottom, and we put in our propulsion mixture at the bottom. Now, for this purpose, oh, I've forgotten, I think we're still reasonably safe. Excuse me, I'm just going to think. Now, by the way, there's a bit of a physics experiment going on with those bottles. You will notice that the three dustbins have three different sizes, and the purpose is to use your intelligence to predict which one should go the highest. All of the lids, by the way, have got string on them, or rather rope, should I say. String would be positively useless, but they have rope on them, and the purpose of the rope is to make sure the lids don't hit the roof of this building. You have been warned. Now, the trick is to try and guess which one goes the highest. Now, I have to take amazing precautions because I've got a deadly high explosive here, gun cotton, nitrocellulose, another brilliant invention of the chemist. The nitrocellulose was developed during the middle of the 19th century, and it makes its use as a high explosive in all sorts of situations. I'm going to just start off because I'm going to be using nitrocellulose to propel my ping-pong balls to the ceiling. But before I do so, I just want to show you how it burns, so you can see roughly. A piece of cotton wool burns like a piece of paper. Nitrocellulose, which is cotton wool combined with extra nitrogen and oxygen groups. Oh, that was okay. So you have been warned. We're beginning. So we carry on watching now. So here is nitrocellulose. That was pretty amazing there. Right, now you saw instantaneous combustion. Now I do warn you, they're going to carry on. Now, yeah, the next thing is, I'm now going to take a small piece of gun cotton here, and please, sorry, I can hear the crackling. It's going to make another bang. I hope you don't mind too much. Now, I'm going to take a small piece of gun cotton. I'm desperately, by the way, I've got a lot in here. If that was all to catch fire, then there would be a real firework in here. Now, please watch carefully. I have a gun cotton cage here. This is for taking the, if I put the cotton wool, it wouldn't go down to the bottom. So this is called a gun cotton cage. We put this in like this, and we drop it into the bottom like this. Et voila, it's reached the bottom. Now we put in ping pong balls, 1, 2, 3, 4, like that. 2 different types of color. We tie it to our stand here, and now we have to put a fuse in. Now I did have my fuses somewhere. Ah, here they are. Here they are. I have a fuse. Now, if you don't mind, I'm going to cut a bit off this fuse. Ooh. My goodness gracious, are we still okay? Okay, I did warn you, this is the last one. That is going to be one hell. Oh. No. But we must carry on, please. I am here. I did warn you. Now, I'm going to now quickly, I'm going to now find my hole and try and, oh dear, I can't find my hole. Oh, I know, it's because I've got my safety goggles and I couldn't see. Here we are, there it is, et voila. So we're now going, so we have now shown you the principles of explosions. I'm now going to, excuse me, put this, I'm sorry there's a terrible mess here, but it doesn't matter, we have to move forward. I'm just going to put this stand here. And now, please watch carefully. I'm going to light the fuse now, and hopefully the ping pong balls will shoot to the ceiling. There will be a little bit of a bang. Shouldn't be too bad though. And please watch carefully. Now, this is the principle of the mortar. I will shortly move to the principle of the rocket. Please watch carefully. There should be a bit of a bang. And the ping. Yes, there they are. There we are. So there we are. Thank you very much. So no, this was just showing you now. I'm now going to illustrate for you the principle of the rocket. The principle of the rocket is fundamentally different from the principle of the mortar. In the mortar, the fuel burns at the bottom and pushes things out. In the rocket, the fuel burns and travels with the actual container. It is the Newton's third law of motion. To every action, there is an equal and opposite reaction. Now, what we're going to do here, now is I've got these so-called Pringles tins or whatever. That's okay. They're called Pringle rockets for short. This is certainly not my invention, but it's rather fun, and I think we should demonstrate. Now, the principle is this. This is all of these are essentially hollow tubes. There is a small hole at the top and a larger hole at the bottom. We're going to fill. I've got Damon here, who's a pupil at Highgate School. Dear Damon, could you come, please, because he's going to help me do this. And thank you very much. And what we're going to do, Damon, we're going to fill these rockets, these tins, one by one with hydrogen, okay? Now, you've got a long tube of hydrogen here. Now, we'll just make sure that we've got no naked flames around because hydrogen burns. So I'm going to listen. I'm going to just set this going. Look, there you are. I tell you what, you turn it on, okay? It's a negative, anti-clockwise, right? So what we'll do is we'll fill these up one by one, okay? Now, what you'll do is, we're filling them. We're just filling them, okay? So what we'll do is we're filling them up. Then you're going to, I'll tell you, you operate the hydrogen, okay? Yeah, okay, right, hold that. Now push it right into the bottom. Push it right to the bottom, okay? And leave it, you're turning it, yeah, that's it, brilliant. Okay, keep going. More, let's have a lot higher. Sorry, we haven't rehearsed this, but it's... Okay. Now turn it on, because I wanted to show people. Yeah, turn it on.
I wanted to tell you that hydrogen has a very low density. So when you talk, it makes your voice sound silly. But that's purely physics.
Sorry, turn it off again. Sorry, I just get carried away. No. There's no point. I think there's no point in wasting a good gas. One must use everything. Yeah, have it going. Yeah, pull it out. Not too fast. You're doing very well. Okay, sorry, we've got to fill these up really quickly. Right, here we go. We'll do a few of these. Now, yeah. Very good indeed. Brilliant. Thank you very much indeed. Thank you very much indeed. We'll just do... And what we then do, we're going to light them all. Keep going. Yep. Now, the interesting thing is, hydrogen, when it's pure, it burns very quietly. However, if you mix it with air, it explodes with considerable violence. Now, keep going. Yeah, keep going, pull it out. Brilliant. Thank you, Damon. And final one here. I bought far more of these. I got hungry for Pringles last night. I had a great Pringles party. Yes, I ate six packets of Pringles. Right, now here we go. Now, there we are. Thank you very much, Damon. Brilliant. Now, no. Now, this is the clever bit. What we're now going to do, because the show must go on, we're going to light these. And Damon, have you got a couple of... Look, there's a candle, my dear boy. Get yourself a couple of... We're going to light these one by one. And then, this is the thing. On the top, there is a small nozzle, and I will spread them out a bit, you know, so it'll be far more fun. Let me get them all the right way up, because if we have them the right way up, then it will work correctly. If we have them the wrong way up, that would be positively stupid. Right, so what we'll do we'll have that one there, have all these. Now, they've got the small nozzle at the top and a big nozzle, a large opening at the... Now, are you able, dear Damien, to follow me around as we light these with a lighted... Let's start this. Let's start here, okay? And you'll light it. Now, keep it alight. And I will take this thing at the bottom. Now, okay, you ready? Yeah. Good. Now, hang around. Good, that's hydrogen burning there. Now we do the next one along here. The next one along here. Oh, sorry, that's okay. That's what happens when it explodes. Are you okay, Damon? I did warn you, there are lots of bangs. Safety specs, Damon. Put on some safety specs in case it goes in your face. Sorry, it's all a bit, you know, these things happen. Damon, are we ready? Sorry. You know, we keep, oh, sorry, the bottoms come off this one altogether. This one might go bang, but let's, go, it didn't go, thank God. Okay, I'm getting terrified of all right. Next one, Damon. Brilliant. Next one, Damon. We're doing, did you like that one? Good. Oh, that's upside down. Idiot Szydlo. No wonder it went bang. Right, here we go. Oh, that's it, yes. They do all sorts of things, you know. They're rather unpredictable. Is it a light? Yes, it is. Well, if it's not, that's too bad. Now, listen, these things will carry on. What happens essentially is as the hydrogen... Oh, that was a weedy one. I'm sorry. In fact, the best one was the one that wasn't meant to go, but it doesn't matter. The point is we're illustrating the principle. Hydrogen, when it's pure, burns with a flame which is completely like this. You'd hardly know anything's going on. But as the air goes in through the bottom, it forms an explosive mixture at a certain point, and then you have this bang and the whole thing takes off. Now, that's the principle of the rocket. The product, which is pure water, goes out of the bottom and the rocket takes off. Now, we can wait for those. I'm now coming on to a little entertainment. We're back to the Waterworks theme. Oh, yes, I did say. There's one more to go. And we're now going to Damon, the violins. We're now doing the clock reactions. Clock reactions basically change color when a certain time elapses. So I'm going to bring on two music stands. You see, I'm afraid I have a terrible admission. I'm sorry, they're rather feeble, some of these, but they do work. I have a terrible admission to make. I just love music. So I love playing the violin for any excuse at all. And this is what we're going to do. We're going to play for you a duet by... let's put the violin. Let's get these out. In my word, there is a lot of mess here. Debris everywhere. But I mustn't trip up. It would be hugely embarrassing to trip up, you see, while I'm playing. Now, we're playing a violin duet by the Czech composer, Bohemian composer, Jan Kalivoda, who wrote many beautiful, beautiful pieces. He wrote over 250 compositions. And while we're playing the duet, you should observe some beautiful color changes here. My dear boy, Damon, could you kindly just help to move a few of these things back? I'll tell you why. Maybe people can see the colors better then. Just purely, let's move things out of the way. Thank you so much, my dear boy. Just move things out of the way because I would like you to be able to enjoy. I think we finished with the candle for today. And I want you to enjoy watching these color changes. We can take our beautiful phosphorus globe with its very useful phosphoric acid inside, beneficial phosphoric. Oh, I've forgotten to do one more thing. Doesn't matter. While we're waiting for that, I will show you, we'll be playing, there'll be two things going on at once. I have some beautiful colors. I forgot to show you about colors in fireworks. And I wanted to tell you the reason, by the way, you are most welcome to dim the lights I'm showing you three different types of color fireworks have always had colors associated with, and that is due to the presence of different metals. Now, I have got here three solutions containing lithium, sodium, and copper compounds. They are dissolved in alcohol, and as they burn, you will observe, hopefully, three different beautiful colors being produced. So we're going to set this on fire now. And while these are burning, now this will take, by the way, 2 or 3 minutes before you see the color. It has to reach the right temperature. And a very important piece of science is this. Every single element, we know over 100 elements, every single element has its own individual, not necessarily flame color, but spectrum. Each flame that you're going to see here, we're going to have hopefully a traffic light sequence. Each flame which you're going to see here is as actually a very unique color. And if that was analyzed by a spectrum, the theory of spectrum, the technique for spectroscopy was developed by the German scientists Kirchhoff and Bunsen in the 1880s. They recognized the fact that if you take the spectral lines from these elements, they are very specific. The copper green is only copper. Barium also has a green which looks looks much the same, but it actually gives you a different spectral line sequence. That, in turn, is due to electron transitions within the atom. These are wonderful techniques that we now have at our disposal. So we'll allow that to burn, and while that is burning, we shall start off our clock reaction and musical. Now, Damon, are you okay for picking up your violin? Is everything okay? You can see clearly? We can see the music. Okay, Damon, are you ready to go then? Okay, and what should happen is, as we play, the colours change, and our trick is to try and finish when the last colour changes. It's a sort of thing, it's unlikely, but we're going to do our best, okay? So, are we ready to pick up one each? No, one of these each, right? Okay, one of these each, then we stir. We haven't practiced, by the way, so you have to realise that. So, ready, steady, pour. Yep, all in, brilliant. Right, now we stir them. Now we stir them. Okay, finish now. Right, so now we're ready to go. We've had our percussion, and now we're playing our duet. Relax, Damon, plenty of time. There isn't any time, but who cares? Are you ready? Okay. There we are. Thank you very much, Damon. Thank you very, very much. We almost got it. Thank you so much indeed. Absolutely brilliant. Thank you. Thank you very much indeed. And there we are, the traffic lights, you see. Right. Thank you very much indeed. And now for the final experiment. One more to go. Now, may I suggest, if anyone is of a nervous disposition, definitely leave. You will regret it if you stay here and you're nervous, okay? Because this is the final big bang of the thing, and we shall have everything possibly. This is, please remember, fireworks has been the theme for the evening. So here we have now my favorite experiment, my most favorite. Now, dear Damon, can I please ask you to help to clear? Oh dear, look at those beautiful traffic lights. They're still burning. Damon, we've got to try and clear, I'll tell you what, all this stuff from here. I'll tell you what, let's try just gently moving it to the back, because this is now the final thing. Just move them all to the back. I will grab our fountain. We will grab our fountain, and thank you very much indeed for your patience. We really have, whoops-a-daisy, I almost fell over. That would be most embarrassing. Now, I'm going to make up a fuse powder of magnesium ribbon, magnesium powder rather, which is a very, very violent flash powder. You mustn't look at this directly. I have to warn you, this is very, very, very damaging for the eyes if you look at it due to the huge amount of ultraviolet radiation. Dear Damon, could you please wear glasses just in case, okay? Thank you very much. Just carry on wearing goggles as a matter of course. Now, there will be total pandemonium here after this has happened, and I'm going to thank you very much. Just gently then, you're doing brilliantly. Phenomenal. Right, there we are. There we are. That's that one there. And here we are. There we are. There we are. Now, ooh, that's probably a bit too much potassium chlorate. Let's put a bit back. Sorry. We have to get the proportions about right. What they've done is they've... yes, now... It is quite important. That's it, Damon, you're doing very well. Keep going with that. I'm going to now lay the trail. Now, I do have to say, this makes a huge cloud of white smoke. It will rise up and it will totally fill this amphitheatre. So I have to warn you. Now, it's only magnesium oxide, which is not... Do you know what? I'm a little concerned. Do you know what I'm going to do? Brilliant. I'm going to move these balloons closer in. Let's just make sure. Yep, I'm going to move them closer in. That's much better because that then is much more sensible. Let me get some... Where's that gaffer tape gone, my dear boy? Where did we put it? Sorry, we've got to tape this. I'm doing this, by the way, in the interests of common sense because there's no... It's okay, I found some. Okay, we'll use this instead. The point is there's no point in making the thing too long. Right, here we go. I think that's reasonable. I think that is now reasonable. And what I'll do is I'm going to lay the fuse powder along here. Now, what happens is the fuse powder goes along like this. And it is a flash powder, which means it burns amazingly rapidly with a very, very high temperature. And that means it is definitely not to be, and that will be the last experiment. Now, for this purpose, let's just be... I'm just double checking. Damon, you're phenomenal. Far better than I could have dreamt in a million years. Now, we need the potassium permanganate and glycerine, my dear boy. We had them here. I've got, where is the potassium permanganate and glycerine? Ah, here it is, both together. Fantastic. Now, may I once again... Just warnings, there's going to be a very bright flash, okay? So please don't look at this directly, okay? It is a very bright flash, and there will be two enormous bangs. These are filled with a mixture of hydrogen and oxygen, which is the main ingredient that is used to propel rockets to the moon and out into space. So it is the maximum violence, possibly, etc., that you can imagine. So, is everyone okay? Are you all braced for what will be very loud bangs, a cloud of smoke? The whole theatre will be filled with a dense white smoke. Here we go. We're using our potassium permanganate and glycerine mixture. Our oxidizing agent is chlorate, and our fuel is magnesium. And here potassium permanganate is there. Now, we need to have an appropriate melody for this. And there it is. Thank you very much indeed. I have finished. Thank you very much indeed. Thank you very much indeed. We're not. Thank you. Damon, can you come and take a bow? Thank you very much indeed. My good friend Damon. Thank you very much, Damon. It was absolutely fantastic. Let me shake your hand. Thank you very much indeed. I bow once again. Take a bow with me. Take a bow with me. We're ready, steady bow. Thank you very much indeed. Thank you very much indeed. Thank you very much. Fireworks and Waterworks, we bow humbly.